A temperature is an objective comparative measure of hot or cold. It is measured by a thermometer, which may work through the bulk behavior of a thermometric material, detection of thermal radiation, or particle kinetic energy. Several scales and units exist for measuring temperature, the most common being Celsius, Fahrenheit, and, especially in science, Kelvin. The coldest theoretical temperature is absolute zero, at which the thermal motion of atoms and molecules reaches its minimum. Classically, this would be a state of motionlessness, but quantum uncertainty dictates that the particles still possess a finite zero-point energy. In addition to this, a real system or object can never be brought to a temperature of absolute zero by thermodynamic means. Absolute zero is denoted as 0 K on the Kelvin scale, minus 273.15 degrees Celsius on the Celsius scale, and minus 459.67 degrees Fahrenheit on the Fahrenheit scale. The kinetic theory offers a valuable but limited account of the behavior of the materials of macroscopic bodies, especially of fluids. It indicates the absolute temperature as proportional to the average kinetic energy of the random microscopic motions of those of the constituent microscopic particles, such as electrons, atoms, and molecules, that move freely within the material. Temperature is important in all fields of natural science, including physics, geology, chemistry, atmospheric sciences, medicine, and biology, as well as most aspects of daily life. Effects of temperature. Many physical processes are affected by temperature, such as physical properties of materials including the phase, density, solubility, vapor pressure, electrical conductivity, rate and extent to which chemical reactions occur, the amount and properties of thermal radiation emitted from the surface of an object. Speed of sound is a function of the square root of the absolute temperature. Temperature scales. Temperature scales differ in two ways: the point chosen as 0 degrees, and the magnitudes of incremental units are degrees on the scale. The Celsius scale is used for common temperature measurements in most of the world. It is an empirical scale. It developed by historical progress, which led to its 0.0 degrees Celsius being defined by the freezing point of water, with additional degrees defined so that 100 degrees Celsius was the boiling point of water, both at sea level and atmospheric pressure. Because of the 100-degree interval, it is called the centigrade scale. Since the standardization of the Kelvin in the International System of Units, it has subsequently been redefined in terms of the equivalent fixing points on the Kelvin scale, and so that a temperature increment of 1 degree Celsius is the same as an increment of 1 Kelvin, though they differ by an additive offset of 273.15. The United States commonly uses the Fahrenheit scale, on which water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit at sea level atmospheric pressure. Many scientific measurements use the Kelvin temperature scale, named in honor of the Scottish physicist who first defined it. It is a thermodynamic or absolute temperature scale. Its 0.0 K is defined to coincide with the coldest physically possible temperature. Its degrees are defined through thermodynamics. The temperature of absolute zero occurs at 0 K equals minus 273.15 degrees Celsius, and the freezing point of water at sea level atmospheric pressure occurs at 273.15 K equals 0 degrees Celsius. The International System of Units defines a scale and unit for the Kelvin of thermodynamic temperature by using the reliably reproducible temperature of the triple point of water as a second reference point. The triple point is a singular state with its own unique and invariant temperature and pressure, along with, for a fixed mass of water in a vessel of fixed volume, an autonomically and stably self-determining partition into three mutually contacting phases: vapor, liquid, and solid, dynamically depending only on the total internal energy of the mass of water. For historical reasons, the triple point temperature of water is fixed to 273.16 units of the measurement increment. Kinetic theory approach to temperature. A more thorough account of this is below its theoretical foundation. Kinetic theory provides a microscopic explanation of temperature, based on macroscopic systems being composed of many microscopic particles, such as molecules and ions of various species, the particles of a species being all alike. It explains macroscopic phenomena through the classical mechanics of the microscopic particles. The equipartition theorem of kinetic theory asserts that each classical degree of freedom of a freely moving particle has an average kinetic energy of kBt2, where kb denotes Boltzmann's constant. The translational motion of the particle has 3 degrees of freedom, so that, except at very low temperatures where quantum effects predominate, the average translational kinetic energy of a freely moving particle in a system with temperature T will be 3 kBt2. It is possible to measure the average kinetic energy of constituent microscopic particles if they are allowed to escape from the bulk of the system. The spectrum of velocities has to be measured, and the average calculated from that. It is not necessarily the case that the particles that escape and are measured have the same velocity distribution as the particles that remain in the bulk of the system, but sometimes a good sample is possible. Molecules, such as oxygen, have more degrees of freedom than single spherical atoms. They undergo rotational and vibrational motions as well as translations. Heating results in an increase in temperature due to an increase in the average translational kinetic energy of the molecules. Heating will also cause, through equipartitioning, the energy associated with vibrational and rotational modes to increase. Thus, a diatomic gas will require more energy input to increase its temperature by a certain amount, i.e., it will have a greater heat capacity than a monatomic gas. The process of cooling involves removing internal energy from a system. When no more energy can be removed, the system is at absolute zero, though this cannot be achieved experimentally. Absolute zero is the null point of the thermodynamic temperature scale, also called the absolute temperature. If it were possible to cool a system to absolute zero, all classical motion of its particles would cease and they would be at complete rest in this classical sense. Microscopically, in the description of quantum mechanics, however, matter still has zero-point energy even at absolute zero, because of the uncertainty principle. Basic theory. Temperature is a measure of a quality of a state of a material. The quality may be regarded as a more abstract entity than any particular temperature scale that measures it, and is called hotness by some writers. The quality of hotness refers to the state of material only in a particular locality, and, in general, apart from bodies held in a steady state of thermodynamic equilibrium. Hotness varies from place to place. It is not necessarily the case that a material in a particular place is in a state that is steady and nearly homogeneous enough to allow it to have a well-defined hotness or temperature. Hotness may be represented abstractly as a one-dimensional manifold. Every valid temperature scale has its own one-to-one map into the hotness manifold. When two systems in thermal contact are at the same temperature, no heat transfers between them. When a temperature difference does exist, heat flows spontaneously from the warmer system to the colder system until they are in thermal equilibrium. Heat transfer occurs by conduction or by thermal radiation. Experimental physicists, for example Galileo and Newton, found that there are indefinitely many empirical temperature scales. Nevertheless, the zeroth law of thermodynamics says that they all measure the same quality. Temperature for bodies in thermodynamic equilibrium. For experimental physics, hotness means that, when comparing any two given bodies in the respective separate thermodynamic equilibria, any two suitably given empirical thermometers with numerical scale readings will agree as to which is the hotter of the two given bodies, or that they have the same temperature. This does not require the two thermometers to have a linear relation between the numerical scale readings, but it does require that the relation between the numerical readings shall be strictly monotonic. A definite sense of greater hotness can be had, independently of calorimetry, of thermodynamics, and of properties of particular materials, from Wien's displacement law of thermal radiation. The temperature of a bath of thermal radiation is proportional, by a universal constant, to the frequency of the maximum of its frequency spectrum. This frequency is always positive, but can have values that tend to zero. Thermal radiation is initially defined for a cavity in thermodynamic equilibrium. These physical facts justify a mathematical statement that hotness exists on an ordered one-dimensional manifold. This is a fundamental character of temperature and thermometers for bodies in their own thermodynamic equilibrium, except for a system undergoing a first-order phase change such as the melting of ice, as a closed system receives heat without change in its volume and without change in external force fields acting on it. Its temperature rises. For a system undergoing such a phase change so slowly that departure from thermodynamic equilibrium can be neglected, its temperature remains constant as the system is supplied with latent heat. Conversely, a loss of heat from a closed system, without phase change, without change of volume, and without change in external force fields acting on it, decreases its temperature. Temperature for bodies in a steady state but not in thermodynamic equilibrium, while for bodies in their own thermodynamic equilibrium states, the notion of temperature requires that all empirical thermometers must agree as to which of two bodies is the hotter of that they are at the same temperature. This requirement is not safe for bodies that are in steady states though not in thermodynamic equilibrium. It can then well be that different empirical thermometers disagree about which is the hotter, and if this is so, then at least one of the bodies does not have a well-defined absolute thermodynamic temperature. Nevertheless, any one given body and any one suitable empirical thermometer can still support notions of empirical, non-absolute, hotness and temperature, for a suitable range of processes. This is a matter for study in non-equilibrium thermodynamics. Temperature for bodies not in a steady state. When a body is not in a steady state, then the notion of temperature becomes even less safe than for a body in a steady state not in thermodynamic equilibrium. This is also a matter for study in non-equilibrium thermodynamics. Thermodynamic equilibrium axiomatics. For axiomatic treatment of thermodynamic equilibrium, since the 1930s, it has become customary to refer to a zeroth law of thermodynamics. The customarily stated minimalist version of such a law postulates only that all bodies, which when thermally connected would be in thermal equilibrium, should be said to have the same temperature by definition, but by itself does not establish temperature as a quantity expressed as a real number on a scale. A more physically informative version of such a law views empirical temperature as a chart on a hotness manifold, while the zeroth law permits the definitions of many different empirical scales of temperature. The second law of thermodynamics selects the definition of a single preferred absolute temperature, unique up to an arbitrary scale factor, whence called the thermodynamic temperature. If internal energy is considered as a function of the volume and entropy of a homogeneous system in thermodynamic equilibrium, Thermodynamic absolute temperature appears as the partial derivative of internal energy with respect to the entropy at constant volume. Its natural, intrinsic origin and null point is absolute zero, at which the entropy of any system is at a minimum, although this is the lowest absolute temperature described by the model. The third law of thermodynamics postulates that absolute zero cannot be attained by any physical system. Examples of temperature